Let's answer a few of these questions. You're measuring weights of rocks that are uniformly distributed, population with a mean of 20 pounds, with a standard deviation of 3.2 pounds. Consider the distribution of sample means, where the sample is collected using an unbiased, simple random sample. Okay. So again, notice I want an unbiased, simple random sample. Why? Because I'm about to use this fact, and the sampling distribution must be unbiased. So even if a question says I'm just sampling, assume that it's an unbiased sampling process. The sample size is 2. What are the values of the parameters shown below for the sampling distribution? The sampling distribution of the mean will have a, so what will be the mean? Well, if my random sample is unbiased, then what do I have here? Looks like the mean weight is going to be 20 pounds. And my standard deviation is 3.2 pounds. So what will be the mean? Well, according to theory, it should also be of the sampling distribution of the mean. So this is, again, mean of sampling distribution of mean. It should be 20 pounds. And what will be the standard deviation? The standard deviation should be 3.2. My sample size is 2. It'll be that. Okay, and that's exactly what it will be. So I'm not going to calculate it for right now. Okay, get to another one here. Consider the distribution of sample means. Again, it's the distribution of all possible sample means. When the sample is collected using an unbiased simple random sample, the sample size is 8. What are the parameters shown below for the sampling distribution? The sampling distribution of the sample mean will have the mean will be 20 pounds. Why? Because the population mean is 20 pounds. What about standard deviation? Well, it'll be the population standard deviation divided by square root of 8. Okay, so let's answer the next question. Does the value of the population mean of the sampling distribution of the mean change depending on the sample size? Right. So it's a little confusing here. Maybe I'll get rid of the word population. Does the value of the mean of the sampling distribution of the mean change depending on the sample size? The answer is no. Because look, it was a sample size of 2, it was 20. A sample size of 8, 20. No, it will stay exactly the same. Consider the distribution of sample means where the sample size is collected using 5-year-old kids to select rocks from a pile of rocks and bring them back. So what the heck is this population about? You're measuring the weight of rocks that are uniformly distributed. Okay, by the way, what is a uniformly distributed population? It's this. It looks like a rectangle. So it looks like this. If I had to draw a picture of it, it looks something like that. If I sampled here and created a histogram, it would look something like this. It will be different heights, but relatively all the heights are about the same. So it would look something like that. So uniform just means all the way across, you have exactly the same chance. I mean, everything's equally likely, what it comes down to. So right now you're measuring rocks. The distribution of these rocks are, again, all the way across from however big to however small is completely uniform. Now consider distribution sample means with a sample collected using 5-year-old kids to select rocks from a pile of rocks and bring them back. The sample size is 8 equals 8. What do you surmise would be the mean of the sample distribution of E of X bar? So now we're going to go, what is E of X bar? Okay. So what are we talking about? We're taking 5-year-old kids. We know that the mean weight of the population is 20 pounds with a standard deviation of 3.2 pounds. Now, that's the average weight, but then you see the variability here. It's uniform, so it's not going to follow the 68, 95, 99.7 rule, but you can start getting an idea of how far things could work away. So the kids are going to, 5-year-old kids, are they going to grab a 20-pound rock, the biggest thing they have? Probably not. I mean, there's always some kid that always tries, right? There's always some 5-year-old kid that's, I want to grab the biggest thing and try to bring it over. But most of the kids are probably going to be very, very cautious. And maybe after they pick up the big rock, go, yeah, forget about that. And let me just grab this rock. And so now what I surmise is that this mean will be less than the population mean. Why? Because kids I should point to this. Kids are not randomly selecting rocks. Their process is biased. And I'm putting a lot of thought into what is going through these kids' heads, or at least a theoretical. And I'm just going to assume that the kids are going to go, you know something? Yeah, I'm not going to bring that biggest rock. This small rock is good. Like maybe it'll go here because it's a 14-pound rock. And it's still pretty heavy. I mean, it is pretty heavy for a 5-year-old kid, but they're going to try and, I mean, you must bring a rock back. So they're going to now start realizing that the rocks are heavy and they're going to go for small rocks. So whatever the mean turns out to be, if let's say that we did this forever, nothing but 5-year-old kids, each time picking up 8, and we did this like 80,000 times, each sample consists of 8, I would bet that the mean now of the sampling distribution would be less than the population mean. Why? Because this process is biased. Okay, that's what bias is. You're favoring a particular outcome just by the way you're doing it. If the sample size is increased to 32 using an unbiased sampling method, what is this? Well, the mean of the sampling distribution will be, again, 20 pounds. What about the standard deviation? Well, it should be 3.2 divided by square root of 32. Notice that the sample size started at 2, then 8, now 32. How is the sample size increasing? Let me see, how is it increasing? Well, let's see. I'm noticing something. 2 times 4 is 8. Oh, no, I'm noticing 8 times 4 is 32. How is the sample size increasing? Sample size is quadrupling. Each time. How does that affect standard deviation or X bar? I don't know. I haven't really thought about that. Let me just check. 2.26. So I got 2.26 for my first, 1.13, and 0.565 for my third. So I definitely could see that it's going down. But now that I'm looking at it, it looks like 2.26, 1.13 is half of this. So in other words, this is 2.26. It's just half of this. This amount is half of the previous. Is that true for the next one? 0.565. If I take, this is true, 1.13 divided by 2, do I get this? And again, these are approximations. And the answer is yes. So what's happening is, how does that affect standard deviation? I can start seeing that every time n is quadruple, standard deviation is cut in half. This is very, very, very important. So you have to quadruple it just to cut this in half. So for example, if your n is 1,000 and you want your standard deviation to be half of its previous amount, then you need to increase to 4,000. What if you wanted to cut it in half again? Well, if you want to cut in half from whatever this result got, then you need to then quadruple this. So now we're at 16,000. So every time you want to half the standard deviation, half the variability, you need to quadruple the sample size. And this sort of explains why eventually we stop, we don't go much further, because as you saw when I was playing with my little draw the sample, try and get the standard deviation, get closer and closer to the other one. Sure, I was adding 10,000, but relative to the sample size that was there, about 4, adding 10,000 is nothing. To do some significant damage, I needed to, for example, if it was 100,000 and I wanted to get closer, I need to go not 10,000 more. I need to go 400,000 now to get half as the variability. So this is a very important fact, and we can actually just mathematically understand this. So if I call this SD of X bar, what happens to SD of X bar if I do this? I take SD of X, and instead of having n, I go 4 times that. Well, just doing a little bit of algebra. Remember, I'm going to take the square root. I'm going to separate these two. Square root of 4, square root of n, and when I find the square root of 4, I get the 2. So notice if I could put over here one more time, I'm going to take this and just bring it over here and try and get it. So notice if I now quadruple the sample size, what will happen? Then now the new standard deviation will be half of the previous amount. Previous amount was when it was just n, quadrupling it, now cut this thing in half. That's what it's saying.